right, let's get started with 4 quadratic expressions, and we're going to be factoring them in this section. So this should be something we've seen before in Algebra 1, and so we're bringing it back here and looking at it again. So what we're going to learn, find common and binomial factors of quadratic expressions, and then we're going to factor special quadratic expressions, so special patterns that we'll see a few times. So a couple phrases for our vocab to be on the lookout for: factoring, greatest common factor of an expression, perfect square trinomial, and the difference of two squares. All right, so a couple of things we'll need. So let's check our skills here. Simplify each expression. Let me do 1, you do 2 and 3. So number 1, I see x squared, but I don't see any other x squareds. I see x and 4x, so let's combine our like terms, and then minus 1 on its own. Number 4, 2x is going to distribute. You guys can do this. 2x times the 5 is 10x. And then don't forget to distribute that negative in there, negative 2x squared. All right, so go ahead and finish up 2, 3, 5, and 6. When you're ready, let's get started with the lesson. All right, factoring. So factoring is rewriting an expression as a product of its factors. So factoring is splitting things up into all the pieces, right? Smallest pieces. The greatest common factor of an expression is the common factor with the greatest coefficient and the greatest exponent, right? So the biggest thing that goes into two different things. For instance, the greatest common factor of 10x cubed and 5x squared would be 5x squared, right? The biggest coefficient and the biggest exponent that goes into both of your terms, all right? So let's take a look at this. Let's factor both of these. So 4x squared plus 20x plus 12. So what can come out of these? So we can pull a 4 out, and then we're left with x squared plus 5x, and then minus 3. And we would be done there because it doesn't factor any further, at least without a quadratic equation, which we haven't gotten into yet. How about the second one? 9 and 24, both factors of 3, and n squared and n, we can pull an n out front. So then we're left with 3n minus 8, and we would have them both factored. So let's see if you can do it on your own. 1, A, B, and C, give it a shot. All right, so let's factor quadratics here. So the trinomials are ax squared plus bx plus c. When we have all three parts, an a, a b, and a c, we're going to factor this into two different binomials, all right? So we'll do a couple different examples, different situations when we have positives and negatives, the different ones here. But the way I like to read this is we need to multiply to the last number, we need to add to the middle number, and then we need to figure out our signs with that. But here we're multiplying to positive 7, we're adding to positive 8. Find two numbers that work for that. Find two numbers that multiply to 7 and add to 8. Well, there's really only one way to multiply to 7 with two numbers. That's 1 and 7. And so we've got x and x, because x times x is x squared. And we want positive 7 and positive 8. So it would factor as x plus 1 and x plus 7. See if you remember how to do this yourself. 2a, b, and c. Give it a shot. All right, what about when we have a positive and a negative here? So now we're multiplying to 72, and we're adding to negative 17. So let's see if we can figure that out. What are two numbers that multiply to 72 and add to negative 17? How about 8 and 9? So we'll have our x's, and now our job is to figure out the signs. Well, if we multiply to a positive, the signs must be the same, but if we add to a negative, those signs must both be minuses. So x minus 8 and x minus 9 is what we would have here. Your turn again, 3a, b, and c. All right, how about when we have a negative and a negative? So now we're multiplying to negative 12, and we're adding negative 1, right? So we have to have a difference of 1 here. If we're adding to negative 1, that's also known as subtracting to 1. So how do we get to multiply to 12 and subtract to 1? How about 4 and 3? Let's figure out our signs. If we multiply to a negative, we must have one positive and one negative. And when we put them together, we want the negative to end up retaining there when we add them. So the bigger number, the 4, must be the negative. Negative 4 and positive 3. Your turn for A, B, and C. All right, so now it's a little trickier when we have a coefficient in front of the x squared. So on these, we need to factor the x first, right? So 3x squared. So in this one, we're really not multiplying to 5. We're multiplying to 15, and then we're adding to negative 16, right? So on this one, 15 and 1 are going to do the trick, right? How would we use factors of 5 and factors of 3 to get 15 and 1? We would have to have 3 times 5 and 1 times 1. So with our rules of FOILing, we know it's going to be 3 times 5 and then 1 times 1. So those are where the numbers would go. We know that we need to multiply to a positive, so both signs are the same. And since we add to a negative, both of those signs are negative. So we'd end up with 3x minus 1 and x minus 5. So a little trickier here. See if you can figure out how to factor A, B, and C for understanding check number 5. All right, so now trickier again when we have negatives and we have a coefficient here. So this could either be 1 and 4, or it could be 2 and 2. And 15 could either be 1 and 15, or it could be 3 and 5. So a lot of different options here. We're multiplying to negative 60 4 times the 15. And then we're going to add to negative 4, otherwise known as subtracting to 4. All right, so let's think about how we could multiply to 60 and have a difference of 4. Right? So 60 could be 15 and 4, but that doesn't have a difference of 4. How about 10 and 6? There it is. 10 and 6 has a difference of 4. So let's look at these combinations. Right? Is there any way to use those with pairs and get 10 and 6? Well, how about 2 times 3 for the 6? And how about 2 times 5 for the 10? So let's set this up. The 2's were with the x's, right? Those 2's were with the x's, so we've got 2x and 2x. And then we had 3 and 5. All right, so on this one, we know that the signs are different. One's a positive, one's a negative. And when we add them, we're going to end up with a negative. So we want the bigger number to be negative. So it's a negative 5 and a positive 3. A lot going on there, right? A lot of pieces to put together. See if you can do it for 6A, B, and C. All right, so second objective here is our perfect squares. And so on these, if we have this pattern, a squared plus 2ab plus b squared, we're going to be able to write a plus b squared. And if we change it to a negative in the middle, we'll have a minus b squared. And so we'll see that in this problem here. 9x squared minus 42x plus 49. 9's a perfect square, 3 times 3. 49's a perfect square, 7 times 7. And if we check on this, 3 times 7 is 21. Look at this, 42 is twice that, okay? So we know that this is going to be a perfect square because it fits that pattern of 3x squared. Right, let's go back and look at the pattern. 3 squared x squared, that's your a squared, right? If we go back here, okay? A squared, and then we have 2 times 21x, it's a minus 2 times 21 is 3 times 7x, and then plus 7 squared. And no x's on that one. Right? So that's the pattern. ax squared minus 2ab. This is a, and this is b. So our result here is going to be 3x minus 7 squared. Now, if you didn't follow the pattern, that's all right. We could just factor it like normal here. Going back to the beginning, we need to multiply to 49 times 9. Right? So that's 450 minus 9, that's 441. Right? And then we need to add to negative 42. Well, that's kind of tricky, but we see 3 and 3 and 7 and 7. We're willing to bet it's going to be 3x minus 7 and 3x minus 7, which, if they're both the same, turns into the squared, which it is. All right, so a little trickier, but see if you can follow the pattern. See if you can do that for 7a, b, and c. All right, and now let's look at our last thing, factoring a difference of 2 squares. So if we have perfect squares, a squared minus b squared, we get to split them up with an a plus a b and an a minus a b. All right, so let me give you one example before we go into the real world problem. If I have x squared minus 64, this is x times x, this is 8 times 8, and so our answer factored is going to be x plus 8 and x minus 8. All right, so that's how you would work the formula, work the pattern. Let's look at this word problem here. The photo at the right shows the cross-section of a pipe. Let's find the cross-sectional area. So we want to find the area of this pipe in 2 dimensions. And the pipe, not the inside of the pipe, we would just want this part, right? That's the actual pipe. So let's figure this out. Well, we know all the way to the edge is 1 circle, right? And so the area of that, let me do it in the same color with green. That circle is going to be pi r squared, but we know it's 3 squared. And then we're going to take away the inner circle. So minus the inner circle goes out like this, but only r. We don't actually know that dimension. So minus pi r squared. We've got 1 circle minus another circle, and the difference is going to be what's left of the pipe on the edge. Let's clean this up. We've got 9 pi minus r squared pi. So let's factor out the pi, and then we're left with 9 minus r squared. And so what did we just learn about the difference of 2 perfect squares? This could be pi, 3 minus r, right? 3 times 3 is 9, r times r is r squared, and 3 plus r. And that's going to be your completely factored cross-sectional area of this pipe. All right, so see if you can do some factors of perfect squares. That's the last thing to do. If you've got that, fantastic. If you've got questions, make sure you're asking them in class. I'll see you then.